This is Chapter 9, covering solutions. A solution is a homogeneous mixture, and so you may recall that a homogeneous mixture is a mixture that is the same throughout. Examples are ocean water, clean ocean water, blood plasma, and soda. You've got two pieces to a solution. You've got a solute and you've got a solvent. The solute is something that is getting dissolved, and the solvent is something that does the dissolving. So the solute is getting dissolved, and the solvent is doing the dissolving. We call water the universal solvent, so you can think about that. So those two parts make up the solution. The solute that's getting dissolved is typically the one a lower percentage of, so a lower amount, and the solvent is going to be the greater amount. Okay, so looking at some solutes, so here's an example of a copper 2 sulfate solution. So you've got water and copper 2 sulfate. Water is in the background, just the white background, and then the copper 2 sulfate are the blue is copper and the gray is the sulfate. And so you see the water coming down to the copper 2 sulfate, and then it's coming down here and it's breaking up and kind of dissolving, right, the copper 2 sulfate. You can have solutions of solids and gases, you can have solutions of liquids and liquids, you can have solutions of solids and solids, and so here are some examples of that to take note of. Please know that air is a gas in a gas solution. It is mostly nitrogen and partly oxygen, so the solvent would be the nitrogen because it's the one that is the most. We call water the universal solvent because water has that great polarity and it has those hydrogen bondings with itself, but it also has this positive and negative end to it, and that can attract the positive and negative charges of ionic compounds to break them apart. So we like to say that in determining what kind of things dissolve, like dissolves like. So polar things will dissolve polar things, nonpolar things will dissolve nonpolar things, and so we're building upon this. You need to know how to predict the polarity of a substance so that you can tell whether or not it will be dissolved in something polar like water or something nonpolar like oil. And so when you're deciding that something gets dissolved, you need to look at the interactions that are going to occur. And so we've got a few different interactions that need to occur. You have your solvent-solvent attraction. So what is the attraction between these two water molecules? This is a hydrogen bond. Now, it's not always a hydrogen bond as your solvent-solvent attraction. It's whatever intermolecular force you're dealing with. Then you have your solute-solute attraction. And so for this example, because it's an ionic compound, it's an ionic bond. And ionic bonds are very strong, but they can be broken. These attractive forces between positives and negatives can be separated because what is the strongest force here on this page? Well, that's the force between the water and the sodium and the water and the chloride, because we know that the sodium chloride dissolves, and so the solvent-solute attraction must be the strongest attraction. This is an ion dipole attraction here, and it's very strong. And sometimes the ionic bond is stronger than the ion dipole, and the thing does not dissolve, and you know that. You have a list of things that do and do not dissolve in your periodic tables. So this is another image just showing you kind of how things dissolve. Dissolution is kind of violent. The water comes up and it rips the sodium and chloride ions apart from each other, then it surrounds the sodium and chloride ions. Take a look at how we're surrounding each of these. And so if you notice that the sodium ion is positive, so all the negative ends of water are attracted to that. So the water surrounds it in a specific way, versus the chloride ion is negative, and so the water is surrounding it in a different way to hold that attraction true. So just more images of the ionic compound dissolving in water. So here's some solutions with polar solutes. If you have methanol, methanol is an alcohol. Methanol is polar, and so methanol also has hydrogen bonding because it has this OH bonded to together, and you put water and methanol together, you still get some hydrogen bonds. And so the hydrogen bonds are being shown here in the red highlight. And so you get water and methanol dissolving together because they're very similar with their types of bonding and with their polarity. So you can pause and do a learning check here if you want. Identifying the solute in each of the following solutions. So the solute is going to be the thing that's less. And so I'm going to highlight here the answers. The solute here is your sugar. The solute here is your methyl alcohol. The solute here is your sodium chloride. And the solute here is your oxygen. Pause and do a quick learning check. When solid lithium chloride is added to water, it dissolves because the lithium ions are attracted to what? Well, the lithium positive are attracted to the oxygen atoms, and the chloride ions are attracted to the hydrogens. Opposites attract. Another quick learning check. Which will dissolve in water? Will sodium sulfate dissolve in water? So check your periodic table. We'll see that's all sodium. This is the group 1 metals, and they are soluble. And so you can say, yes, that will dissolve in water because your periodic table says it's soluble in water. So that's how you can use that. You can also think about an ionic compound as most of them will dissolve in water because ionic compound is like very, very polar, and so that will dissolve in the water. So like dissolves like says ionic will be polar. Gasoline is nonpolar, so it will not dissolve in water. So not soluble. Iodine. It says polar or nonpolar. Well, if you have 2 iodine particles, and if I draw a Lewis structure here for you, you'll see that it is nonpolar, and so it is not soluble in water. What about hydrogen chloride? It says polar or nonpolar. This is polar. I could draw my dipole here like this, and so it will be soluble in water. If you have substances dissolving in water, you can sometimes get electrolytes. And so some substances dissolve into an electrolyte and some substances do not dissolve into electrolytes. Electrolytes are substances that dissolve into ions. And those ions, they conduct electricity. And so an electrolyte is a solution that conducts electricity. If you dissolve into ions, that is called dissociation. So here's an example of electrolytes versus non-electrolytes. 2 things that dissolve in water. Sodium chloride dissolves in water, and sugar dissolves in water. But sodium chloride dissolves into ions, and the sugar dissolves into sugar molecules. So the sugar is not an electrolyte because it doesn't make any charged particles, and the sodium chloride is an electrolyte because it makes charged particles. Strong electrolytes make charged particles, and so they will conduct electricity very well. So here we have an image of a conductivity tester, and we see that the sodium chloride solution will conduct electricity. A soluble ionic compound or a strong acid, we'll learn more about strong acids in the next chapter, are strong electrolytes. A weak electrolyte is something that gives a little bit of ions. And so if you look at hydrofluoric acid here, it is being shown to you as breaking apart in 2 directions, meaning it doesn't go 100%. If we look at the previous one, we see that it goes one way. That means that as soon as you drop sodium chloride in water, it breaks 100% into sodium and chloride ions. This means that the hydrofluoric acid goes both ways, and so it's got some HF left together in the solution and some as ions, and only actually 1%, around 1%, will break into ions. So we call this a weak electrolyte because does it make ions? Yes. But is it good at making ions? No. So it's weak. So your weak acids, and we'll talk about those in chapter 10, will be your weak electrolytes. And then you have your non-electrolytes, and these are things that do not dissolve into ions. Does it dissolve? Yes. but not into ions. And so you have covalent compounds that might dissolve in water, they don't dissolve into ions, or you can have things that don't dissolve. So insoluble ionic compounds or insoluble covalent compounds, if they don't dissolve in water, you can't dissolve into ions because you don't dissolve at all. So here's a classification of some different electrolytes and some examples. So this is a multiple choice learning check. Pause and do this one. Okay, you've got to complete each reaction for strong electrolytes. So if this is a strong electrolyte, what is it going to look like? So how does this calcium chloride break down? And this is just like how we made calcium chloride in the first place. We're going to break it down that way. And so I see that I'm going to make one calcium ion and how many chloride ions? Should be 2 chloride ions here, and that's how we write this. Chloride is not a polyatomic ion. Chlorine is diatomic when it's by itself, and here it's not by itself, so I have to write it as its actual ionic form, which is Cl-, not Cl2-. Here we have potassium phosphate. It will dissolve because potassium is a group 1 metal. So how many potassium ions do I have? I have 3. So how do I write 3 potassium ions? The answer here is A. Do not do this where you break down each part of a polyatomic ion. You need to write ions breaking apart like you would write ionic compounds coming together. So refer back to chapter 6 for that. Let's do a quick learning check, pause, and come back. Which of the following reactions represent the dissociation of a strong electrolyte in water? So a strong electrolyte is going to be either an ionic compound or a strong acid. And so looking here, do I see the dissociation, the breaking apart of a strong electrolyte? The answer here is C. Oh, I'm crossing it out, not highlighting. The answer here is C. So here, this is a weak electrolyte. We will talk about that a little bit later when we talk about bases, but this is a weak base, and so it doesn't break apart 100% into ions. This is a covalent compound, not an ionic compound. And again, this is a covalent compound, not an ionic compound. Sodium sulfate is your only ionic compound that is soluble. Write the equation for the formation of a solution for each of the following. So we're going to write down how this breaks apart. So pause and do this one. Now you've got potassium chromate. So potassium chromate is going to break into how many potassium ions? 2 potassium ions. What's the charge of potassium? Plus. And how many chromate ions? This is not chromium and oxygen separately. This is 1 chromate. So that's how this will break apart. The partial dissociation of the weak electrolyte, phosphoric acid. So phosphoric acid is partial. So we can write it in a double arrow. And I get 3 hydrogens, and I get 1 phosphate. So it does break into ions, just it goes back and forth. It's not strong in one direction. And then you have sugar. So how would I write this? I would say the sucrose solid turns into, I can't break this down at all because it's a non-electrolyte. So I'm just going to say, well, now it's turned from solid to aqueous because it's dissolved. That's the only thing that you can do for those. So if you get an electrolyte, we can measure something called an equivalent. If you've ever done an electrolyte screening for yourself or for a patient, then you've seen the reports for that screening are in electrolyte or equivalents. So those are the units. And so sometimes you see milli equivalents per liter, and that's going to be a concentration, an amount of a certain electrolyte in a patient's blood. So an equivalent is the amount of an electrolyte or an ion that provides 1 mole of electrical charge. So I can tell the equivalent by looking at the charge of the ion. And so if you look at this chart, you'll see that you've got your ions, you've got your charge, and you're looking at the equivalents per mole. And so how can I write the equivalent? I can say, well, this is in 1 mole. So 1 equivalent per mole, 2 equivalents per mole. If your charge is 2, you've got 2 equivalents. If your charge is -2, you also have 2 equivalents. And so equivalents don't care if my charge is positive or negative, it just cares what my charge is. And so if you know the charge, then you know the equivalent per mole. That's a conversion factor that you can then use. So how would I do this? calculating equivalence. You're going to use conversion factors and mole ratios to get equivalents for things. How many moles of calcium are in 0.5 liters of blood? The patient's blood has a calcium level of 8.8 milliequivalents per liter. So go ahead and rewrite this as a conversion factor. So a milliequivalent, just like a milliliter, I can write 1,000 or 10 to the 3 milliequivalents is equal to 1 equivalent. And if I'm talking about calcium, I also have another conversion because I know calcium is 2 plus, and I know that 2 equivalents equals 1 mole. Because that's what an equivalent means. It's the charge of equivalence is equal to a mole. So how many moles are in liters? So I'm trying to go from moles to equivalents, equivalents to milliequivalents, milliequivalents to liters. This will get me there, and I can set it up. So I have liters of blood. In 1 liter, you've got 8.8 milliequivalents. In 1,000 or 10 to the 3 milliequivalents, you've got 1 equivalent. And you've got 2 equivalents per 1 mole. And so we should get 0.0022 mole of calcium ions here. So if chloride is the only other ion present, what would the concentration of chloride be? And so if I have calcium and chloride, how is it going to come together? Calcium is going to come together with chloride in a 1 to 2 ratio. So it'll be calcium chloride. And so for every 1 mole of calcium, there's going to be 2 moles of chloride. And so if I'm trying to find the concentration of milliequivalents of chloride, I can start with the concentration of calcium and use a mole-to-mole ratio as my center. Now, 1 liter is going to stay. So we're going from a conversion to another conversion. So a little bit more difficult with the math setup. You're not going to get rid of the liters, and we're not going to be using this 8.8 milliequivalents per liter as a conversion, but actually as a starting place. We're trying to take the milliequivalents of calcium and turn it into milliequivalents of chloride. But the liters of blood are the same. So I'm not going to cancel out the liters of blood, but I do want to cancel out the milliequivalents. And so 10 to the 3 milliequivalents of calcium is 1 equivalent, right? Because I'm going through the same thing we've done before, and I can write this out for you, but 10 to the 3 milliequivalents is equal to 1 equivalent. 2 equivalents of calcium are equal to, of calcium are equal to 1 mole of calcium. Then I have a mole ratio, and let's talk about chloride's conversions. And so for chloride, the charge is 1, so it's 1 equivalent of chloride is equal to 1 mole of chloride, and then we use the same milliequivalent conversion at the end to get that. And so if I'm looking at calcium now, I will say that I know that 2 equivalents of calcium is equal to 1 mole of calcium. And then I know that 1 mole of calcium is equal to 2 moles of chloride. And I know that 1 mole of chloride is equal to 1 equivalent of chloride. And I know that 1 equivalent is equal to 10 to the 3 milliequivalents. And so here I'll just do a quick conversion check. I've got equivalents canceling, moles of chloride, moles of calcium, equivalents calcium, milliequivalents, and I'm left with milliequivalents per liter of chloride. And if you notice this, everything gets canceled. So my 10 to the 3 is canceled, my 2's cancel, and so the answer is exactly the same. This is true for all ionic compounds. If you're in an ionic compound, because your mole-to-mole ratio cancels out your equivalents, you will, because your charge tells you your mole-to-mole ratio, right? The ratio between the two things is determined by the charge, and so is the equivalent determined by the charge. Then your amount of equivalent concentration per liter will be the same for both ions in an ionic compound. That's kind of just a short trick that you can use if you're solving a problem with it. And so there are certain concentrations of equivalents in electrolytes in blood plasma. There's a charge balance you need to maintain, and it varies depending on what you need for your patient. So here's just some certain IV solutions that you would maybe use for a patient, and looking at these. Look at the units for these concentrations. It's milliequivalents per liter. And so you need to know what an equivalent is if you're going to be giving a patient an IV, and on that IV bag it's labeled something about an equivalent. It's telling you about how many charge really per liter, like what is the electrolyte balance of that. So go ahead and do a quick pause and check. In 1 mole of iron 3, how many equivalents are there? There are 3 equivalents because there's a charge of 3 in iron 3. In 2.5 moles of sulfate ions, there are how many equivalents? So we're going to do a little quick math. In 2.5 moles of sulfate, how many equivalents are there? Well, in 1 mole of sulfate, how many equivalents are there? There are 2 equivalents because the charge is 2. So we have 2.5 times 2, which is 5 equivalents. If an IB bottle contains sodium chloride, if the sodium is 34, the chloride is also 34. The ionic compound has the same milliequivalents per ion. When you're talking about things dissolving, you have to talk about solubility. Some things dissolve at different temperatures and some things dissolve at different pressures. It depends on the substance you're talking about. And so uric acid in the blood can dissolve more than it's supposed to. It's supposed to be a solubility of 7 milligrams per 100 milliliters of plasma. And if you have more uric acid than that, then you exceed the solubility, which means the uric acid doesn't flow in the blood, and that can cause gout. So solubility is a conversion factor, really. It's how much solute can be in that amount of solvent. It's temperature sensitive, so it depends on the temperature. You can get more or less solute to dissolve. So here's a graph that's showing you this. And so as we look at this graph, we can see that as you increase the temperature, the solubility, how many grams you can fit in 100 grams of water, increases drastically for most substances. Check out sodium chloride though. If I increase the temperature, my solubility doesn't rise too much. And so gargling salt in warm water doesn't really increase the solubility too much of gargling salt in cold water. It is very similar for sodium chloride. But for other salts, they're ionic compounds, so we call them salts. You have a very increased solubility with the increase in water and increase in temperature. And so this is for solid compounds to dissolve in water. The warmer, the better it dissolves. What about gases in water? So check out this image. I have 2 sodas being poured here. I want you to think about the temperature of the sodas. Which soda is colder? Which soda is warmer? So you're thinking, hopefully, well, this soda on the right is colder because it has more bubbles, right? Because carbon dioxide is actually more soluble in water at cold temperatures. And so the solubility of a gas increases with increasing pressure, so we have to pressurize carbon dioxide, but we also have to cool it down so the carbon dioxide gets trapped in the water. And so I apply my carbon dioxide under pressure, and then when I open my can, it will release that pressure. And sometimes it'll take the liquid with it if I'm not careful, and that will kind of cause the liquid to come out of the can very fast. So you can have solutions, solubility where your solubility is maxed out, or you can have solutions where your solubility is not maxed out, or solutions where your solubility is more than maxed out. And so if your solubility is totally maxed out, you're at a saturated solution. And so a saturated solution holds exactly how much it can hold at that time. If you add more, it will not dissolve. It will just kind of go to the bottom of the container. If you have an unsaturated solution, you don't have as much as you could possibly have. If you add more, it'll just dissolve. And if you have a supersaturated solution, then you are currently holding more than you can, and it is very easy for it to come out of solution. And so here's an example of a saturated versus unsaturated. I know that the sample on the right is saturated because there is solid at the bottom of that container, and so I know that the water is holding all it can't hold anymore, and the rest of it is getting dropped to the bottom. You know these solubility rules. You do not have to memorize them. They're on your periodic tables, and so this will tell you whether or not the ionic compound will dissolve in water. So here are some ionic compounds that do not dissolve in water. They make colorful solids. Give a pause and see if you can name these. These are named cadmium sulfide. You can't really see that, huh? So cadmium sulfide. Iron 2 sulfide, lead 2 iodide, and nickel 2 hydroxide. Always practice that when you can. So, predicting products. You guys have already been doing this for your lab for reactions, but we're going to go over it just a little bit here. So go ahead and pause and see if you can tell me what this reaction is. Alright, so hopefully you're able to write this reaction. If not, we can go over it together in class and office hours. The aqueous potassium iodide with lead 2 nitrate solution. So if you're looking here, this should be your answer of your reactants and your products. So what did I do? So I looked at my reactants. These are my reactants here. So I have potassium iodide and I have lead 2 nitrate. And when I break them down, they break into ions. Lead ions, nitrate ions, potassium ions, and iodide ions. You do not break the nitrate apart. It is one thing. So I have some possibilities of things I can put together. So right before anything comes together, we put it into a beaker together, and then some things maybe are gonna meet and make a solid. Which things are gonna be a solid? And so when I'm looking at these original compounds, I'm going to be switching up these charges here. And I have some possibilities. I have the potassium chilling with the nitrate. And I have the lead that's going to chill with the iodide. One goes with the other because you can't put two positives together, two negatives together. You still need your charges to balance out. And so I need to look here and say, okay, what's the state of matter for these? So now I look at my periodic table and I look at my solubility chart and I see that well, any nitrates and any potassiums are always aqueous because they're always soluble. And then halides, chloride, bromine, iodide, those guys are soluble except for silver, mercury, and lead. And so this will be your solid. It's insoluble. It will make a solid. It will not dissolve in water. And so you get the lead 2 iodide coming out as a solid. We'll see that as a precipitate. Pause and predict the reaction between aqueous potassium iodide and sodium chloride. So you actually get no reaction here. It's no reaction because your products are the same. So what does it mean to have sodium chloride, aqueous? It means sodium ions and chloride ions, kind of just floating around. And it means potassium ions and iodide ions, kind of just floating around. Well, I can put the sodium and the iodide together, but they're still just kind of floating around in the solution. And I can put the potassium and the chloride together, but they're kind of just floating around in solution. So everything's still floating around. Nothing did anything special, so it didn't show me any chemical reaction. So if everything is all AQ, you get no reaction. And so once we're thinking about how we're going to make solutions, aqueous things, what things are aqueous, what things are not aqueous, what things would be solutions, what things will not be solutions, we need to know how can I measure out the concentration of a solution. And so here's a sample, or here's just an example of a process. So if we take 5 grams of potassium iodide and add it to a 1 liter volumetric flask, which is the flask over on the right, enough water is added to the flask to make 1 liter. And so if I have 1 liter of a solution, and I put in 5 grams of potassium iodide, then I have 1 liter of the potassium iodide solution. So you can express the concentrations as amount of solute versus amount of solution. So this is kind of, you can think about it as like the beginning of a percent. It's a part over a whole, right? It's the part that I'm interested in, the solute, over the whole thing. And so I have a few different units I can use: mass percent, volume percent, mass volume percent, and molarity. So the mass percent is a percent with mass. The mass is grams, and so you're going to use grams of solute over grams of total, which is solute plus solvent. If you have a percentage and you assume 100 grams of the total, you get rid of that 100% in the math, and you can use it as a conversion factor. And I will show you how to do this in class. But you can use your mass percent as a conversion factor if you assume 100 grams of your total. And that's true of any percent, actually. And so if you have 8 grams of potassium chloride to form 50 grams of a solution, the mass percent would be 16. So how do we get this math? Well, if I have 8 grams over 50 grams total, then I do some math and times by 100, I get 16%. And so that's how we are going to show these percentages. You write the percent, and then you'll also put what it is, for mass percent, because both of the units are in mass. But let's say I didn't want to measure the mass, I wanted to measure the volume or something, I could do that too. There's another mass volume percentage. So pause and do a quick learning check here. Alright, the answer is C. So how did I get this? I have my solute here is not the water, because the solute is the one that's in lower amount, so 15 grams over. Now what's my total? My total is 15 plus 235. My total is not the 235. It's the solute over the solution, the whole thing. And so if I do this times 100 to get a percent, I get 6%. Another way you can use concentration of a solution is a volume percent. Same thing as the gram, except now we're talking about milliliters. And so you'll use the milliliters of the solute over milliliters of solution. Assume 100 to get rid of the 100%, so use it as a conversion. You can also use mass volume. So if you wanted to weigh out a solid, but you wanted to put it in water and measure the volume of the solution, you can do that as well. Same thing here. Assume 100 mils of the total to get rid of the 100%. So write 2 conversion factors for each solution. So pause and work that out. For A, you can write 2 conversion factors. Oh, no, I give you, yeah, here they are. Oh no, it's all messed up. And so I'll show you these 2 that you can't see. So here's what you should have written. If you have a conversion, remember you can flip it and you can use it either way. Oh, you can see this one, so this goes here. So how do I turn a percentage into a conversion factor? Assume 100, so put 100 as your base, and then your percent now goes away and it just becomes your top number. Now you've got a conversion factor. But you'll pay attention to these letters to know which units you should use. So molarity, bringing it back to moles, moles are in everything, and so now molarity is going to be a unit that we use, just like the percentages, as a concentration. How much stuff do you have in that solution? So we're going to be using the moles of the solute over the liters of solution. There's no percentage here. It's just straight up conversion factor. You don't have to worry about converting it into a conversion factor. It already is one. So how would you prepare a 1 molar sodium chloride solution? So this means I want my solution to be 1 molar. Now notice that molarity is big M, so don't give me any little m's. Those are actually for something called molality or mass or meters, so be careful. And then don't give me these kind of arching m's either, because that can sometimes stand for molar mass. So I want good pointy capital M's for molarity. So if I want this whole thing, I want to slap a label on this, and I wanted to say 1 molar NaCl, then I would need to add 1 mole of sodium chloride to 1, and add it until I get 1 liter. So we always add water until we get to 1 liter, not add 1 liter, because the sodium chloride actually takes up a little bit of the volume. How do I weigh 1 mole of sodium chloride? Well, I know the molar mass is 1 mole. So here we're connecting everything. So go ahead and give it a try. So pause and try this one. Alright, so calculating the molarity of a solution made by putting 15.5 grams sodium chloride into a beaker and adding water to make 1.50 liters of sodium chloride solution. You can absolutely do this kind of algebraically if you want. I like a conversion factor, so I like setting it up like that. So I'm going to show you here. Alright, so I need to go from, I want molarity. So what is molarity? Molarity is moles over liter, right? So I need those two things. Do I have the liters? Yes, I have the liters. So I know I have the liters, 1.50 liters, so I really need the moles. So let's just find the moles. Well, if I have the mass, I can use the molar mass to give me the moles, yeah? So if molar mass for sodium chloride is 58.44, I use the periodic table to give me that. And it's always for 1 mole, that's just the definition of molar mass. And so I can do a quick conversion here to find my moles. And I get 0.2652293. That's my moles. And I want to divide that by 1.50 liters. And you should get a molarity of 0.177, and big M is your unit here. So go ahead and try it again. Pause and try this. So how many grams of sucrose? So I want to know the grams are contained, and they give me the molarity. Every time you see big M, I want you to cross it out, and I want you to write moles equals 1 liter, because that's really what big M is. It's the moles per liter, so write it as a conversion factor. And so if I have a conversion from liters to moles, and I want moles to grams, I need the molar mass. So here's my molar mass. 1 mole is equal to 342.34 grams of sucrose, and so now I can plug this in. So we'll say 1.72 liters. For molarity, the 1 liter goes on the bottom, and the number of moles is going to go on top here. So now that I have the 1 mole in my molar mass, my 342.34 grams on top, I can cancel all of this out and do a quick little math to get an answer here. 42.34, and I'm going to get 446, yep, grams of sucrose in that amount of that molarity. Okay, so we're just using a new conversion factor here. So go ahead and try one more time. So I want to know the molar concentration. So molar concentration, you need to think this is molarity. So I want to know the molarity of the sodium and the phosphate ion individually. So I can write a mole ratio to tell me this. Now remember, this is how many moles per liter. But I am trying to go from one conversion to another, so I want still the moles per liter. So I'm not going to cancel a liter. All I need to do is cancel out moles. And so looking at this, in every 1 mole of sodium phosphate, how many moles of sodium are there? Well, there are 3 moles of sodium ions, just like when we're doing equivalents. It's exactly the same thing. And in 1 mole of sodium phosphate, how many moles of phosphate? Well, there's 1 phosphate here, not 4. There's just 1. So I can use this and put this together. So I can say, okay, let's do the sodium first. So to do the sodium, I will take 1.50 mole of sodium phosphate over 1 liter of solution. And I will use a mole ratio to transfer my molarity from talking about the sodium phosphate to talking about just the sodium. And so the sodium phosphate will cancel, leaving me the moles per liter of the sodium. And so you'll find that you can do the really quick conversion with molarity just by multiplying by the subscript. And so you get 4.50 molar Na plus. Now for your phosphate, you may have figured this one out already. It's a 1-to-1 ratio, so my molarity is going to be exactly the same. So for every 1 liter of solution, you have 1 mole of phosphate ions for every 1 mole of sodium phosphate ions. So your molarity is going to be exactly the same of your phosphate. So here's just some quick conversions, some examples, a good go-to place while you do some homework on this. Okay, so now we're going to talk about dilutions. Your Dilution is going to be adding water to something. You're going from more concentrated to more dilute. So a serial dilution would be diluted a little bit, then take that dilution and dilute it even more. So that's why this is kind of a joke, serial dilution. You have two equations for dilutions. They're essentially all the same equation, but I want you to know that you may see it in both ways. M stands for the molarity, and C stands for concentration. And molarity is a concentration. So you can just think about using the C1V1. I will use M1V1 by default. As a chemist, we focus more on the molarity than we do mass percent, and mass volume percent. But in the healthcare field, you're going to see more concentration units like the mass percent, so you use that. When you're using a percentage, you just use the percentage. No need to change it out of that. We're going to plug this in like we would a gas law equation and get out an answer. So be careful when you're setting this up, but it should be pretty simple. You always want to add acid to water, AW, not WA. If you are diluting anything in the lab, you always want to add acid to water, never water to acid, because water, some acids dissociating is very exothermic, and sometimes if there's not enough water there to take on some of that energy, it can actually break your glassware because it's very very hot. Okay, so explain how to prepare a 5 liters of a 1.5 molar potassium chloride solution from a 12 molar stock solution of KCl. So we're going to use the M1V1, same as C1V1, it's just we know we're using molarity. So I'm going to walk you through this question and then have you do some practice. So let's establish what we have. Do we have M1s? Do we have V1s? What are they? So I want to prepare this. So this is actually a V2. So I want to have this at the end. And I want my molarity to go with that. So this is your M2 to be 1.5. So it doesn't actually matter which ones you number the same, as long as they are together. So these two go together because of this language of A. From a initial molarity stock solution. So a lot of times we'll have stock solutions that are higher concentration because we can dilute them. So I need to figure out what to do here, and what's missing, my V1 is missing. So let's just find V1 and see if that helps us explain what to do. So we're trying to tell someone how to prepare this. What would we say? So let's rearrange for V1. So V1 is equal to M2 V2 over M1. So we can just plug this in. Now we know my M2 is 1.50. We know my V2 is 5.00. You do not need to change this to liters if it's in milliliters, because we're going to cancel out all of the units anyway. So as long as your units are the same, it doesn't matter, just like in the gas laws, except for Kelvin. So I get 1.5 times 5 divided by 12, and that gives me a V1 of 0.625 liters. And so how would I prepare this? I would say, hey, you've got a stock solution, so I'll draw a little picture. So I have a stock solution of 12 molar. You're going to take 0.625 liters, or 625 milliliters, out of that and put that into a new container. And that new container is going to have 1.5, that new container is going to be then filled up with water. So put this in a new container. So you have your 0.625 of your 12 molar. And then we're going to add water until we get to 5 liters. Now, our total new solution, we'll slap a label on it. We'll say 1.50. So that's kind of how you would explain that problem. So why don't you try using a percentage? If as long as it's the same unit, don't worry about changing it into a conversion factor. Just use it. It'll cancel out. So pause and work on this one. So what volume of a 2% mass volume HCl solution can be prepared by diluting 25 milliliters of 14? And so what volume of this is being prepared? And so we're looking at a C2. This is my new, and I want to know what the V2 that goes with it is. My stock solution is 14%, so this is my C1. and this is my V1. Again, it doesn't matter which ones you label 1s and 2s as long as these two go together. So I'm solving for V2, so this time I'll do V2 is equal to C1 V1 over C2, and I'm going to plug in 14% times 25 milliliters over 2%. Your percents will cancel. You're left with milliliters if that's the unit the question wants, and this one doesn't specify, but multiple choice you'll be able to tell. And let's just see, I think I messed up. Times 25 divided by 2, and you should get a V2 of 175 milliliters as your V2. And so we're going to talk about properties of solutions in the last little bit. When you give someone an IV, you're typically giving them an isotonic solution, which is 0.9% sodium chloride. Iso meaning the same. So isotonic means the same. So isotonic solution has the same solute concentration as your blood. So when you give someone an IV of 0.9%, it's like the body doesn't have any weird reaction to it because it's the same solute concentration as the blood. It's really important that you know that, because if you give a patient a not 0.9% solution, you could kill them depending on what's going on with them. If you give a patient pure water in an IV, it will burst all of their cells. So you have to be very careful about doing this. This is really relevant for you guys. So solutions, going into the details of like exactly what a solution looks like so we can understand this isotonic, hypertonic thing. A solution is transparent. Typically, you can see through a solution. It does not separate, and everything looks the same. It's homogeneous, and it contains small particles, ions, or molecules that cannot be filtered, right? So you cannot separate it out with semi-permeable membranes. You have something else, though, called a colloid. And so a colloid and solutions are kind of hard to figure out. They have medium-sized particles. It still cannot be filtered, but it can be separated by semi-permeable membranes. And so I want you to think about a semi-permeable membrane like your cell membrane. Or we're gonna use a dialysis bag, right? That's a semi-permeable membrane. And so a solution you cannot filter, and everything passes through. Okay, a colloid has a little bit bigger particles, not so big to where they can be filtered, but big enough to where you can actually separate it out with a semi-permeable membrane. So some examples of colloids. Fog is an example. I like to think about a colloid as something that like has these like suspended pieces in it. Any kind of milk, dairy product is a colloid. Blood plasma is a colloid, right? I've got these medium-sized particles kind of floating around in that. You have a substance, this is a good word, dispersed. It's dispersed throughout. You've got these, in milk, you've got this kind of fat that's dispersed throughout the rest of this watery liquid. And then you have a suspension. So a suspension is a heterogeneous. So not talking about a solution or a colloid. A suspension is totally heterogeneous. It has large particles. It can be filtered. So this is like muddy water. Okay, something you have to shake. So I like to say a suspension, a colloid, has small, medium particles and stays suspended. It's hard to tell a colloid from a solution because you don't really have to shake it. But a suspension will settle out. So if you leave muddy water in a jar, it'll settle out eventually, right? That's a suspension. So if something settles, it's a suspension, but if it stays suspended, it's a colloid probably, if you're not sure if it's a suspension or a colloid. So here's some examples and just a very quick rundown of those three things. Again, here's how kind of you would see these images, helping you figure out the difference between those three. All right, last little bit, hang in there with me. Osmosis. First of all, if you haven't watched Osmosis Jones, it's a great movie. You should watch it. Osmosis is really important in our bodies, and so osmosis, water is flowing though, and so we think about the particles as flowing in osmosis, but it's really the water that's flowing in osmosis. Water is always trying to dilute everything. So think about water as like super active in its job. Its job is to dilute stuff, and so if the water sees, oh, there's too much stuff over there, I need to go dilute it, make it less concentrated, the water is going to rush into that side. And so water always flows from lower to higher concentration because it wants to make it more dilute. So think about water as saying there's not enough water over there, it's too concentrated, it's too salty, it's too something, I'm going to rush over there and like help even it out. So if you have the situation in this beaker here, we would actually see the side on the right, the water level would go up because there's sugar on the right side, and there's, the water can flow through. Now the sugar can't flow through because it's a semi-permeable membrane. And so the concentrations will become equal over time because the water is going to rush over to the sugar side and it's going to make the sugar more dilute. So osmotic pressure is the pressure that would prevent the flow of additional water. So like what kind of pressure do you have to make the water stop doing this thing naturally? And it is greater as the number of dissolved particles in the solution increases. And so thinking about the osmotic pressure, if you're dealing with a sample like this, you have pretty high osmotic pressure because it is going to take a lot to stop that water because it's going from nothing to a bunch of sugar. Right? So the more sugar you have, the more the water wants to go. And so the pressure to stop the water would be really high. So your osmotic pressure is the pressure to stop the water from doing what it wants to do. And so, like I said, over time, you would see the water level actually increase. We can use reverse osmosis to filter things, which is actually applying a force to water to get it to go the opposite way that it wants to go. And so that's how we can get pure water sometimes. And so here's an example of reverse osmosis. We apply pressure to the water. Which way does the water want to flow? Water wants to flow into water. Look, water's going into the battle. Water wants to flow into the salt water. But we're going to force it to flow the opposite way, and that's going to keep the contaminants on the left side, and the water will be fresh on the right side. So that's reverse osmosis. So we talked about isotonic before, just a few more slides. Isotonic means the same as your cells. And so in an isotonic solution, this is what your red blood cells look like. It does normal red blood cells, water flowing in and out at the same rate. Here are some percentages for isotonic solutions. I've also given you something called an osmolarity on your equation sheet for an isotonic solution, but we won't be using that. I'll replace that with the 5 and the 0.9% if you need it. So a hypotonic solution. So what happens in hypo? Hypo means less, right? And so this is lower solute concentration. So if you were to put normal cells in lower concentration than normal, so here it's the same concentration inside and outside. Here it's a lower concentration outside. So this is like pure water. Okay, so if I were to give a patient pure water IV, this is what happened to their cells. So we have higher concentration inside or outside. Well, hypotonic solution means lower concentration outside, higher concentration inside. Water flows to the higher concentration. So which way is the water going to flow? It's going to go into the cell. It flows into the cell, and it can burst the cell because the cell can't take on that much water. And so this is called hemolysis, the lysing, right, the bursting of blood cells. And the opposite is called a hypertonic. So hyper means more, right? So it's more concentrated on the outside of the cell, less concentrated on the inside. So which way is the water going to flow? The water is flowing out of the cell. So the water is going from the cell to go dilute the rest of the concentration of the solution, and that leaves the cell shriveled up, called crenation. In dialysis, we're actually wanting some particles to move through the membrane. And so osmosis is the water moving through. Dialysis is the actual pieces moving through. And so waste particles like urea are removed from the blood using this dialysis idea. So we take the urea we have the urea in our blood, right? The solution particles can go through the semi-permeable membrane, but the colloid particles, like big proteins and starches, they cannot go. Red blood cells cannot go. And so this is how we will eliminate from our kidneys. So here's a picture of what happens in dialysis. The urea being removed from the blood and the blood being pumped back into the patient's body. So give me a quick pause and learning check and telling me whether or not these solutions are isotonic, hypotonic, or hypertonic. Remember that we'll go back up and we'll copy this down. 5 for glucose and 0.9 for sodium chloride. And so doing this learning check, remember that isotonic, and I will have this information for you, is 5 for glucose and 0.9 for sodium chloride. You should probably know that if you're going into the healthcare field, but I'll have it on a periodic table for you for the next exam, or I'll have it written on the exam for you as well. So give a pause and look at this. Okay, so if I'm 2% sodium chloride, is that greater than or less than the isotonic? Well, if 0.9 is isotonic, 2 is greater than 0.9. So this is hypo or hyper? Hyper. It's more. So my cells would do what? Crenate. Good. So 1% glucose solution, is that less, the same, or more? Well, this is less than the 5%. So this is hypotonic. And so your cells would lyse, right? Hemolysis. 0.5 sodium chloride. Well, it's pretty close, right? But it's not exactly the same. And so it's a little bit less than 0.9. So it's a little bit hypotonic. And then you have 5, which is equal to the isotonic, which would be aisotonic. All right, one last slide, one last check. Okay, so hopefully you've done this one. Always do before we go over the answers. 5% glucose solution. Will my cells change? This is no change because this is isotonic. 1% glucose. Well, that's less than isotonic, right? And so this is hypotonic. And I want you to think about the O in hypo, like what happens to the cells. So this would be hemolysis because they get really big and they burst. 0.5 sodium chloride. So again, 0.5 is hypotonic. So this would be bursting. And 2%, well, that's way more. That's hyper. And so I want you to think about the R and hyper like a cell that's crenating. It's getting all shriveled up. Okay. All right, that is chapter 9.